So now let's proceed to the P and N junction. So how does P and junction work? P and junction are fabricated from a monocrystalline piece of semiconductor with both P-type and N-type region in proximity at a junction. The transfer of electrons from the inside of the junction to holes inhalated on the P side of the junction produces a barrier voltage. So we have here the diagram A and B, which is the A diagram is the semiconductor P-N junction in a circuit, while the B diagram graph is the graph showing a symmetric current and voltage relationship. So next, a key principle is that in many semiconductor devices, the conductivity of a material is controlled by concentration of impurities, which can vary greatly from one region of the device to another. One example is a PN junction at the interface between one region of the semiconductor containing a P-type impurity and another region containing an N-type impurity. One way to create a PN junction is to supply an N-type material to a very clean surface of the P-type material. So since you can't match surfaces at the atomic level, you can't glue the P and N-type parts together expect the bond to work as expected. So we have here the formula of the PN junction, where I is the current, E is the quantum charge, the K is Boltzmann constant, and T is the absolute temperature. So qualitatively, the behavior of a diode in PN junction can be understood based on the conduction mechanism in two areas. Assume connecting the positive pole of battery to the P region and negative terminal for region N. Then the P region is at higher potential than N in the area corresponding to the positive value of V in the equation and the resulting biography. So the field is in the direction from P to N, and this is called forward direction, and the positive potential differences is called forward bias. It flows easily through the N region and transitions to free electrons. It flows easily into regions N and is plentiful in region P. This charge transfer is direct current. Connecting batteries with opposite polarity reverse them. The displacement, the field tends to push electrons from P to N and holes from N to P. However, there are few free electrons in the P region and few holes in the N region area. As a result, the reverse current is much less than there is an equal potential difference in the forward direction. So the figure above is the PN junction in equilibrium with no externally applied field or potential difference. The generation and recombination currents exactly balance. The Fermi energy is the same on both sides of the junction. The excess positive and negative charges on the N and P sides produce an electric field in the direction shown. So the P side, or the pink in the left side, has an excess of negative charge and is at a lower electric potential. So, negatively charged electrons have higher energy bands here. Then, the N side, which is the blue right, has an excess of positive charge and is at a higher electric potential. So, negatively charged electrons have lower energy bands here. Then apply a forward voltage that is above positive potential difference V intersection. The forward voltage reduces the electric field in the transition region. It also reduces indifference between P side and N side energy level. So the figure here showing if the PN junction under reverse bias is thin enough and electrons can tunnel from valence band to the conduction band. And the process is called Zener breakdown. Under reverse bias conditions, the potential difference between the sides P and N of the junction is greater than at equilibrium. If this difference is large enough, the lower part of the conduction band may actually be below the top of valence band on the P side. So we have here the figure showing the semiconductor devices and light. So the LED light emitting element that emits light visible to the human eye, such as purple to red or white. The light receiving device, the photodiode, light receiving IC, etc. products that output changes in light as electrical signals. And the photocouplers, composite device package with a light emitting device and light receiving device, products that transmit electrical signals while keeping them electrically isolated. The fiber couplers, a product that performs electrical to optical conversion and vice versa for communication using an optical fiber. So we have here the reverse semiconductors. Semiconductors to transform electricity to light, and the semiconductor to transform light to electricity. So in recombining, the electron can emit a photon with energy approximately equal to the band gap. This energy can be varied by using materials with different band gaps. Here, the material absorbs photons and electron holes pair are created. Pairs are created in the p-n junction or close enough to migrate to it without recombining are separated by the electric field we described above that sweeps the electrons to the n side and holes to the p side. So another semiconductor devices and light is the photovoltaic cell. Such a device is often called a solar cell, although sunlight isn't required. The production of low-cost photovoltaic cells for large-scale solar energy conversion is very active field of research. So in figure 24 shows such a P-N to P transistor. When there is no current in the left lobe of the circuit, there is only a very small current through a resistor R because the voltage across the base collector junction is in the reverse direction. So when When a potential VE is applied between emitter and base, pulse travels from emitter to the base. So we have here in figure 25 a common emitter circuit. The current in the collector circuit is controlled by the current in the emitter circuit. In addition, the power consumption of R can be significantly higher than the power supplied by the battery to the emitter circuit. Therefore, the device acts as a power amplifier. If the potential drop across R is large, it could be a voltage amplifier. In this configuration, the base is a common element between the input and output sides of the circuit. Another widely used configuration is grounded emitter circuit shown in figure 25. In this circuit, the circuit on the collector side of the circuit is much higher than the current in the base side, resulting the current gain. So we have here in figure 26, the p-type silicon has insulating layer of silicon dioxide, the gate, n-type source, and n-type drain. The current from source to drain is controlled by potential difference between the source and the drain by the charge on the gate, and no current flows through the gate. Field effect transistors are important type. In a variant, the plate is made from p-type silicon with two n-type region on top, which are called sources and drains. A metal conductor is attached to each. The third electrode, called the gate, is separated from the plate, source, and drain by the insulating layer because one of the p-n junction is reverse biased. Now, apply the positive charge to the gate. It is an order of magnitude larger and requires very little charge to provide the substantial electric field. So therefore, the current in and out of the gate is negligible. The P material does not have many free electrons, but there are some, and the effect of electric field is to attract them to the positive gate. As a result, the electron concentration near the gate increases significantly, allowing current to flow between the source and drain. The current is very sensitive to the charge and potential of the gate, and the device acts as an amplifier. So, the device described here is called the enhancement MOSFET. It means it is the metal oxide semiconductor field effect transistor. Now let's proceed to the superconductors. Superconductivity is the complete loss of all the electrical resistance at low temperatures. This section associates superconductivity with solid structures and energy band models. Superconductivity was discovered in 1911, but in theory, it was not well understood until 1957. That year, American physicists John Bardeen, Leon Cooper, and Robert Schrieffer published the theory of superconductivity, and now known as BCS theory. He received the Nobel Prize in Physics in 1972. So this was Bardeen's second Nobel Prize. He shared his first work on the development of transistors. The K to BCS theory is the copper pair which is triggered by the interaction of crystalline cations. It is an intersection between the pair of conduction electrons, and here's a rough qualitative picture of what's going on. So, a free electron exerts attractive forces on nearby positive ions, pulling them slightly closer together. The resulting slight concentration of positive charge then exerts an attractive force on another free electrons with momentum opposite to the first. At ordinary temperature, this electron pair interaction is very small in comparison to energies of thermal motion, but very low temperature it becomes significant. So the pairs of electrons cannot individually gain or lose very small amounts of energy as they would ordinarily be able to do in partly filled conduction band. Their pairing gives an energy gap in the allowed electrons' quantum levels, and at low temperature, there is no enough collision energy to jump this gap. Therefore, the electrons can move freely through the crystal without any energy exchange through collisions. That is with zero resistance.